Alright, so today we're going to be continuing learning about sequences, and if you don't know anything about sequences, I highly suggest you look at the previous video about the basics. Because today we're going to be looking at two specific types of sequences that we'll see a lot, especially in the lens of calculus. So I'll introduce the first one. There we go. Arithmetic sequences. Maybe you've heard of this before. We're still not quite ready for the calculus part of it, but we're building up to it. So I'll write the definition in blue. So this is the definition. Let me just say a sequence, which is just any sequence, is an arithmetic one if it is written in this form. And that form, so I'll write the first few terms. This is what the first few terms are. A, right? That's the first term. A plus D, A plus 2D, A plus 3D, right? And we want to continue this thing, right, to the nth term. And the way we write the nth term is A plus n minus 1D, right? And the reason why it's n minus 1 is because looking at the first term, right? The first term, there's no D, right? So we need this term to be 0, and the only way by that is having the n minus 1 factor, right? If we look at the second term, we have to have only 1D, and the only way to get that 1D is with using n as the kind of like the input is 2, having 2 here instead of, so that's why we have n minus 1D. So that's a important thing to know. And then it also can be written like this, another form. So this is the explicit form if you want to think of it like this. And the recursive is a n minus 1 plus d 4, and I have to add the condition n is greater than or equal to 2. Remember from last video I talked about that n had to be greater than or equal to 2. I had to put that condition because if you plug it in n any less than 2, then the whole thing falls apart, right? So this is what a arithmetic sequence is in the form of. And notice we're just adding, and we're adding kind of like adding. So here I'll give you an example. So if I go from 1 to 2 to 3 to 4, right? And let's say I just keep going actually. So keep going off to infinity. The pattern is, so any term is given by the first term, which is 1, plus what the difference is between the two, which is, so it's n minus 1. What's the difference between 2 and 1? It's just 1. So this is what D functions as. It is the difference between two consecutive numbers, right? So you can take any of them, from here to here or from here to here, right? It's a distance of 1. So we put 1 here and it doesn't really matter, so we can just put it away. And then we can simplify this to be plus n minus 1, which is just n, right? So the nth term is just whatever number n is, right? That's an easy example. So we'll look at one example about arithmetic series. So what I want to do here is do it this. Okay, so I want to find D, which is known as the common difference, right? Every pair of numbers have the same difference. That's what defines an arithmetic series. I want to find B. I want to find the 9th term. I want to find, what else do I want to find? The recursive rule for an nth term, right? Any term I give you, can you find it using a recursive rule? And then finally I want to find the explicit rule. This one's probably the most you'll see. The explicit rule you'll probably see the most often, and that's the most important because we can just plug in any number from there. So I'm going to do it in purple again. So the sequence that I'm going to give you is this sequence. So I'm just going to write it like this. It's the natural log of 2, the natural log of 6, the natural log of 18, the natural log of 54, and so on. And when you look at this the first time, it's kind of surprising seeing a natural log as an arithmetic series. It's kind of like, how do they add up the way they do? So let's try to think about it. Let's see. And we can think about it using A. What is the common difference? And the way we do that is by taking the term ahead and subtracting by the term behind, right? ln of 6 minus ln of 2. We can take any pair of numbers. We can even take the 18 and the 6 and we'll get the same answer. So let's look at this one. When you look at this, do you know what the subtraction is? Yeah. So the way you do this is you notice that you can use a log property, and log properties are super important. When it's two logs are being subtracted with the same base, you can simply just divide them. Oops, not 3, it's 2. 2. And put them as one log, right? Which is the same as natural log of 3. You might think that it's not the same for everything else, is it? So let's try 54 and 18. Log of 54 minus natural log of 18. That's just using the log properties, 54 over 18, which is the same thing. So it is the common difference. So this is the common difference, D. If you're unsure if your common difference is correct, I would just suggest doing a different pair of numbers. So that's A. So this is A. We found A. Now what's the 9th term, right? We can just think about it. So these numbers are multiplying by 3, so we have to keep going. What is it? Let's see. What we would do is probably think of it as the recursive thing, or not the recursive one, the first definition, this one right here, right? So we have the first term and we have to keep adding by the common difference and such. So what we should do is by taking this first term, right? How is it with the second term? It's this term, and then we have to add the common difference, right? Add D, which is a natural log of 3, and then the third term would be natural log of 2 plus 2 times the natural log of 3, right? And this pattern still holds. So we keep this pattern going. We get natural log of 2 plus n minus 1 natural log of 3, which is the common difference. And we want to find the 9th term, so we just plug in 9 to this, right? So this is what B is. You can think of it as like this. I'm writing the first couple terms, and then I'm going to write the nth term, just to get a sense of what the sequence is. So we're looking at this one, we want to find 9s, right? A9 is equal to natural log of 2 plus 8 natural log of 3. Right, and then if you really want to, we can combine this natural log of 2 times 3 to the 8th. I'm just using log properties to condense it into 1. And then if you really want to multiply this out, it's natural log of 13,122. That's the answer. That's the 9th term. And we just found it using one of the definition of an arithmetic series. And then C. What is the recursive rule, right? So recursive rules depend on previous terms. So recursive rules depend on previous terms. We know what A1 is, right? A1 is natural log of 2. So how do we get from A1 to A2 to A3? Let's think about that. We had to, looking at our previous answer, B, we see right here, we had to take our previous term, right? These two terms match, this and this match. We had to take our previous term, so I would say n minus 1, and add natural log of 3. And let's see if that holds for the next one. Does this hold if I do this? And if it should, it probably holds for the rest, right? So let's check this out. So the previous term of A2 is A1, so it's natural log of 2 plus natural log of 3, which is equal to natural log of 6. So then the previous term for A3 is A2, so natural log of 6 plus natural log of 3, and that's natural log of 18. And let's see if that sequence matches what the sequence I gave originally, and this is the sequence I gave originally. So it's 2, 6, 18. We have 2, 6, 18, right? So it does seem like it fits the rule, and the way we would write it is you take the nth term, you take the previous term, and you add the common difference, ln3, and then you have to add the condition for n is greater than 2, or greater than or equal to 2. And then you also have to define what a1 is, because if you don't, then this term doesn't make any sense, or the recursive rule doesn't make any sense either, natural log of 3. And then the final one, the explicit one. The explicit one is basically, we kind of did it earlier, but the only thing is we just plugged in part B, we plugged in the value of 9 into it right here. We plugged in 9, so we just want to plug in n instead. So this is a explicit. The explicit rule is saying an is defined as you take the first term, you add this times the common difference, but it looks like B, but it's actually D, I mean. So D, we're looking for the one that is explicit, so it can describe any term you desire, maybe the 100th term, the 5th term, the 6th term. Unlike the last problem, we actually have to plug in 9 here. This time we don't, because it's supposed to be a general rule. So let's plug in what we know. The first term is ln2, and then we do this. This is ln of 3, we found the difference. Let's do some, I guess, do we know, we can do log properties. This is technically a constant, so we can bring it over here. Natural log of 2 plus natural log of 3 and minus 1, right? And then we can multiply them together. And then this is what we can call the explicit rule, and we can always double check it, right? Let's try to double check it with the 9th term. Remember the 9th term with part B? It was natural log of 13,122. So let's try it. A9 is equal to natural log of 2 times 3, 9 minus 1, which is 8, right? Natural log of 2 times 3 to the 8th, which is actually the same as that, 13,122. So we've done all the parts. I'm going to zoom out and so you can see everything. Let me box the answers for you so it'll be more clear. That's the explicit rule, and then this is, that's the recursive one, and this is the explicit. So here's the whole problem at once. Yeah, so in the next one we're going to look at the other series called the geometric series and see what we can do with that, and then we'll start looking at the calculus of sequences. So that's it.